Alright everyone, welcome to Exploring Geometries and Their Basic Assumptions. I'm Paul Landahl, and this is for my senior inquiry research during the winter and spring of 2015 at Augustana. And before we start, I just want to go over some of the goals and questions that I asked during this inquiry. So I was really inspired by Brian Greene's Elegant Universe, which is a book about space and string theory, but I'm not talking about that stuff. I was just wondering, how could I get a better understanding of two-dimensional space, three-dimensional space, and four-dimensional space? So I wanted to start with how can we start with our most basic assumptions and how do we build up from there? And so I wanted to abandon any preconceptions and any intuition I had, and I wanted to do the what if questions and how I can build up from what I know. And I'm going to utilize proofs and build models to show you my results. And I'm not going to prove anything today, but I'm just going to show you the results of my proofs. And so what we're going to do is we're going to go over some topics like the axiomatic geometry and incidence geometry and some finite universes and what models come up from that. Also, we're going to talk about metric spaces and different models of distance, and we'll also bring it back to the complex plane and how tying it all together. And so it's really important to understand that there is a balance between concrete and abstract during this talk. And so I want to start with concrete examples. I'm going to build up to more abstract things. Once it starts to get a little too abstract, I'm going to bring it back down to some more concrete examples, okay? And so that's why I wanted to start with the incidence geometry, because it's, for my research purposes, I chose to start with this most concrete idea, the incidence axioms. And so I'll build up, I'll show you them, and then we'll build up from there to get some deeper things. So it starts off pretty basic, a couple rules about lines and points. The first one says that given 2 points, that there's a line that goes through them. And so if you have 2 points, there's a line that goes through. Pretty straightforward. Also, the second one, kind of similar. If you have a line, there's always going to be at least 2 points on that, distinct points on that line. Then the third one, if you have 3 points, you know, at least one of those points is not going to be on this line that Q and P are on. So R is never going to be on that line. We can't have a universe where all 3 points are on the same line. So I just want to show you some examples of that. So some finite examples. So this is a non-example. It's a 3-point universe, and what we have is this violates the second rule. It also violates the first one, but I'm going to point out the second one, that every line needs 2 points on it. And so we have this here, this model here with 3 points, but this line only has 1 point on it. And so this is not going to work. So to complete it, you're going to make a triangle, and that's going to fulfill all the axioms. So this is the smallest incidence universe that we can come up with. Then we're going to have this 4-point universe, and this looks like a square, but it also violates the first one. 2 given points are incidents with a unique line. And so what about these corner points? They need a line that goes through them, and so a 4-point universe is going to look something like this. And then last but not least, this right here violates the third axiom, that we can't have all the points on the same line. So a 5-point universe is not going to look like just a line with 5 points on it. It's going to look a little different. It's going to look like a star with the lines connecting around the outside. Also, if you rearrange it, you get this cool little 3D shape, just like this. Pretty cool, I think. So if you notice that these axioms don't actually address parallel lines. So if you ask, given a point and given a line, and the point is not on the line, how many parallel lines are incident with that point? And so just by using our most basic assumptions, we cannot decipher logically. So we have to make a couple choices. We have a lot of freedom for possibilities. And so just for a reminder for you guys, parallel means that 2 lines do not share a point. And so I think initially our first impression leads us to this first one, which is Euclidean geometry, and this is the flat world, the world that we're used to, kind of like the space behind me or the computer screen. It's flat. So every line already, so if you're given a line and given a point not on the line, there's only one unique line that goes through that point. So every line is going to have a unique parallel line through a given point. And this is how we have right angles and how we have walls and ceilings and how we have these straight lines, so we can have perfect squares and circles and triangles. And that stuff is cool, but it might only exist on flat space, because what you see, our perception may imply something different. If you take these Euclidean lines like these railroad tracks. We all know that they're equidistant from each other. They're never going to touch because that's how they're built. But for some reason in this picture, our perception shows us that they meet at some point in infinity. It seems to be that these lines may be curved. We all know that we live on a rounded planet, and so if these lines are now described as greater points of greater circles, they're all going to intersect. If you look at this picture here, every line is going to intersect at some point. And so our perception shows us that even these parallel lines in Euclidean space are going to meet somewhere. And so that gives us to our second model, where it's curved globe. It's called elliptic, and there's no parallel lines in this. Any two lines are going to meet, just like our perception showed us with the picture with the railroad tracks. We're going to get a model that looks like this. So given a line and a point not on the line, that other line that goes through that point P is going to intersect L, and no matter what. And so we have a model with one parallel line, which is the Euclidean, and now we have a model with no parallel lines with the elliptic. What if we have a model with two parallel lines? And that brings us to hyperbolic geometry, which personally is my favorite. So if you're given a line L and point P not on the line, there exist two lines, M and N, such that P is incident with M and L. So P is going to have two parallel lines going through it that's parallel to L. And this is really cool because a lot of physicists think that this is the way our universe is shaped, and so some of their observations and perceptions will imply this type of universe, and it's kind of hard to see. So I'm going to show you this Poincaré disk model, which is the typical model for hyperbolic space. And so if you see, we have a line here, and it's kind of curved. Line AB is a little curved, and it's kind of weird. Then if you're given a point not on the line, then you have another line. See, it's parallel. CD never crosses AB at any point. And then again, we have EC, which goes through the point C and never is parallel with AB. It never crosses AB. And so I just want to show you that you can have infinitely many parallel lines that go through C. That's not a proof by any means, but you can see that there's numerous number of parallel lines that go through there. Another thing I want to show you guys in this model is this kind of funny line here, G1, H1. It kind of looks like a half circle, which is kind of cool, but that's actually considered a line. So sometimes lines don't really behave exactly how we want them to in this type of space, and that can be problematic because when we want to address distance, it's not going to behave like we're used to. So I was thinking, how are we going to measure distance when they're not straight lines? Because in calculus, we use this distance formula, or we use a model like this with to measure between two different points. You're going to use slope, so rise over run. You get this distance formula here, and we're going to refer to this distance formula as the Euclidean metric from now on. So in calculus and pre-calc, we developed this Euclidean metric, but if the lines are not straight and not behaving like we want them to, like we're used to in Euclidean space, we're going to have to generalize our notion of distance and kind of broaden it out. So it's not just this Euclidean metric anymore. We're going to need something else. And so what we do is we develop metric spaces, and these allow us to define distance in many other ways besides that Euclidean metric. And for something to be a metric space, it has to fulfill the following three properties. So distance is zero if it's the distance is zero if it's just same point to same point. So the distance from myself to myself is just zero. It's all the same. And that's a given property. The next property is distance one way is the same distance the other way. So distance from noon to midnight is going to be the same distance from midnight to noon. And that has to be a property of metric space. And also the last one is going to be triangle inequality. So the distance from x to y and y to z always has to be greater than or equal to x to z. And this is three things that we just have to assume for metric spaces. These are the three properties that we can use. So let's show you an example. So let's look at the Euclidean metric again. So let's look at the Euclidean metric with its one unit around the origin. And so we're going to get this circle, which is what a circle is. The radius of one unit around the origin in this case. And so you get this circle, which is pretty cool. But let's look at this other metric we have here. It's a little bit different. And we're going to do 1 unit around the origin for this one. And we get this kind of strange drawing. If this is still a circle, using this measurement of distance, it's still a circle because the radius around the origin is always going to be 1. We're just measuring distance a little differently. So visually, this diamond is actually a circle. And that's I think that's kind of strange, and it should confuse you. Because when lines are curved and lines are not behaving like the way we want them to, we're going to need distance, the idea of distance to change too. So it should be kind of strange that we measure things like this, but it is advantageous when we're dealing with non-Euclidean geometries. And so this also brings us to a further level of abstraction called topology. And this type of mathematics is really cool. If we relinquish our notion of distance and do another level of this abstraction, we get into continuity and this rubber sheet geometry of moving functions. It's really fascinating, but I don't really have time to talk about it now. I just wanted to show you guys some cool pictures of it. Let's move on to a more concrete example. And so with this example, it's going to, I might seem like I'm going on a little bit of a tangent, but bear with me here, we'll bring it back. It's kind of hard to consider three-dimensional space from the outside because we're kind of stuck in it, and that's kind of our universe around us. But it's really easy to look at two-dimensional space from the outside, like the board behind me. It's really easy to analyze that. And so we're going to build this new model to exploit some of these things like distance and lines that we're talking about. And so a really powerful way to do this is to have an algebra or a notation. And so our notation is going to be representing every point as a single number in a complex plane. And so the complex plane is going to be imaginary on the y-axis and real on the x-axis. And with this model, we can manipulate points a lot easier than we could without it. And so I want to show you a couple examples of ways we can manipulate points in this model. So we have this w equals z, where z is just the function. And we can translate it, which just means moving it, basically. We can rotate it. We can stretch it out. We can shrink it. Also, we can invert it, which is kind of cool. If you have this line here, z prime, it's going to invert into a circle, which is really cool and fascinating. And to bring it all back, this model allows us to go to the incidence axioms where we started with and manipulate the points and lines. We could actually build what we call a Mobius geometry, which contains Euclidean, elliptic, and hyperbolic geometry all in one. And this model is so powerful because now we're able to do further inquiry on these types of geometry that I was interested in at the beginning with. So overall, we want to take concrete objects that lead us to an abstract question like parallel lines, and we're going to get new models of space, Euclidean and non-Euclidean space, which further warranted questions about distance. We saw lines behaving differently, and I wanted to wonder how can we think about distance differently. And then we built a new, more powerful model to represent our new idea of space with this generalized idea of distance and lines. And so overall, thank you very much. That was my talk. And any questions? No? Okay, bye.